can anyone I think I'm audible to everyone. Drop a message if you are able to see my screen. You're able to see my PPT, right? Hello.
Yes, you are. We can see.
Okay, so the mesh is very, so today's session is on block mesh. So mesh is a very important part of any computational physics method. Uh, for example, computation fluid dynamics or structural dynamics. So why we need mesh is, for example, we want to solve this heat conduction equation on this domain. So because there is no exact solution available for this, we solve this using numerical method. So what we do, we discretize this partial differential equation, and we want to have a lot of linear algebraic equations. So we want to solve these linear algebraic equation using the matrix solvers such that, and we want to choose a mesh. Delta X is mesh. You can see the domain is subdivided into a lot of parts. So we want to see an optimum mesh, or it has a mesh has a lot of properties. We want to have an optimum mesh such that our linear algebraic equation leads to, or at least tends to, the exact PD. All right. So this is how the mesh looks like. So we have divided our domain into several subdomains, or we can call control volume. So typically in finite volume method, what we have is we want to verify that, or we want the conservation equations or conservation laws to be satisfied by default. So for that, we have a control volume or cell center. So this is the control volume. We have a cell center, and we also have a four faces to it. So this is faces are important in finite volume method to for the conservation loss and to calculate the fluxes over the faces. So this is not needed in FVM or finite element method or finite difference method. So you can see we have cell center and we have faces. So we have two things. Okay, so we'll discuss one by one everything. So this is typically a structured Cartesian mesh in which, using the iterative solver, we first solve for the bottommost row or in next direction, and then we move slowly to the slowly to the in y direction. So we move row by row. So we don't need the numbering of you can say, the cell centers. We don't need numbering of that. But there are, when we move to the advanced programming or advanced CFD, so we have, for example, a snappy hex mesh in which you can see the mesh is very complex. So the mesh is not Cartesian structured. It has complex things in it. So sometimes we have things like face merging, and we also in OpenFOAM also capable of unstructured mesh, and sometimes we have structured and unstructured mesh combined. So in those cases, what we have is at the interface. So when we have this, this interface is the interface face of the two cell centers or two control volumes. So this is one. I am showing it separate, but this is only one. So to calculate to say that the flux is either positive or negative, we have to, in these cases we have to define uh, the particular interface belongs to which owner cell and which neighbor cell. All right. So in complex geometries, it is very important, and OpenFOAM by default implements this, that for every internal face or interface, we have one owner and one neighbor cell. All right. So this is kind of numbering each cell, and make sure that the flux that is calculated is either positive or negative based on the owner and neighboring cell. So for every internal face, we have owner and neighbor cell. Keep in mind this thing. So there are uses like we need this neighboring and owner thing we need is for iterative marching while solving in the iterative solver, and it also has a lot of optimization use for the solvers. So this is what typical block mesh looks like. So this is a hexahedral block. There are polyhedral block also you can do in OpenFOAM, but this is typical hexahedral block, which may have straight lines, edges, arcs, or splines. We can so this block mesh thing is capable of doing any mesh, any complex geometry. So, but there are some like complexity comes in when the mesh is geometry is too complex, but we can mesh any geometry using this hexahedral block with s- arcs and splines edges. So what we have, keep in this mind, what we have typically is one cell center. Then we have faces, and for internal faces, we have owner cell and neighbor cell, and then we have boundary patches. So we'll discuss these four aspects one by one. All right. So next, I think everyone is catching up me. If you have any doubt in between, you can just stop me. So, so this is what the blockMeshDict file looks like. So this as you can see the object is blockMeshDict. So first we have scales. First we have defined the scales. So convert to meter 0.1 means it is 0.1 of a meter. So this is just to scale it. Then we define the vertices. These are the vertices of the block. Then we define the orientation of the block. And there we have also have the number of, and then we define the edges. We'll discuss everything. We'll just go through it. And then okay, so this is what typical block looks like. All right. So So first we have the first vertices that is 0, 0, 0, 0. Then we move move in next direction to the point vertices 1, where we have 10, 0, 0. Then we move in y direction and we move in anti-clockwise direction and complete 0, 1, 2, 3. All right. So now we have completed, you can see in the block hex 0, 1, 2, 3 that now we have completed one face or one plane that we move in the z direction. Just make sure you don't do this mistake. So when you're moving in z direction, that is red in color, then you have to move from 0 to the back vertices, that is 4. And the same thing you repeat in the back plane, that is 4, 5, 6, 7. All right. So this is a typical block, and the this hex is how we define the block. So we move like 0, 1, 2, 3. Then from 0 to z direction we go to 4 in the same scenario, and then we move like 4, 5, 6, 7. So you can change the orientation to the anti-clockwise to clockwise, but this 0 to 4 movement should be like this. So now we'll move to the hands-on part. So I already have some test cases here. So, all right, this is test. So first we will go to the cavity. I think everyone has a cavity test case in their run folder. If you don't, just tell me. I'll tell you how to copy and paste. So I hope everyone have a cavity test case in their run folder. I am assuming you guys have it. All right. So first we will what we will do is we look for so this is what 0 is, the initial condition or the boundary conditions. Constant is what contains the meshing part, and this system contains the system for like the information about the solver schemes and timestamp and all these things. So here in system we have blockMeshDict file. You can also keep this blockMeshDict file in this, usually it is in constant part, but in some cases it is also in system folder, so it is okay. So what I want to tell you is, you can, if you go to this constant folder, you will find a polymesh. So I have already run the block mesh, or have already made the block mesh. That's why it is showing me the polymesh folder. So it has boundary, faces, neighbor, owner, and points. It has information about everything. All right. So first what we will do is we'll open the terminal, and then we'll clean this mesh. So there is command in OpenFOAM. You have to run foam c clean poly polymesh. So when you enter this command foam clean polymesh, it will clean the mesh that was made before. So you can see that polymesh is still there. Hold on, hold on. I think I have opened the. constant, it is saying cleaning dot slash constant polymesh. It should be cleaning, but it's not cleaning. I don't know. Yeah, it is. There is nothing in it. So in polymesh folder is now empty, right? So this this command, keep in mind, clears the previous mesh. Now we'll go to the block mesh part. If you have any doubt, please let me know. If you are not following, please let me know. I'll stop. All right. If you are not following, let me know. So this is typically the cavity case in which we have vertices like this. So vertices are like define this only. We have 0, 1, 2, 3, and 4, 5, 6, 7. So this is here we have 0, 0, 0. That is vertices 1. Vertices 0. All right. Now typically like this, we have this vertices 2, vertices 3. This is vertices 1. This is vertices 2. And like this. This is the last vertice, that is vertices 7. Okay, so these are the vertices that we have defined. Now this hex part is how we define the our block. So as I told you here, how we define the block is first we move in x direction, then we move in y direction, then we planar complete the plane by 0, 1, 2, 3. Move by writing 0, 1, 2, 3. You see 0, 1, 2, 3. All right. Then we move in another direction, that is z direction to the back plane, and we do the same 4, 5, 6, 7. That is 4, 4, 5, 6, 7, 6, 7 in the back face also. So this orientation, this write up, that is 0, 1, 2, 3, 4, 5, 6, 7 is completes our definition of the block. So here it is very simple because it is simple 0, 1, 2, 3, 4. But when you have multiple blocks, then it is very tedious to do, and you have to know the exact like exact orientation of your block and exact method of how to define the block. So the second part is how many grids you want. So I'm saying writing here is 20. That is we want, let's say 10. So we want 10 10 grids in x and y direction. So this 10 typically defines nx, that is number of division in x direction. And this second defines number of division in y direction. Third defines number of division in z direction. So I'm also keeping everything at 10, 10, 10 for now. All right. This simple grading we'll discuss later. So now what we will do is we'll go to this folder. Now you know that we have already cleaned the previous mesh. All right. Now we have already cleaned the previous mesh. So we'll run a command that is blockMesh. It's very simple. BlockMesh. So I have run the command blockMesh. I hope everyone else has run it. So now then you can check mesh. Do this check mesh. So it will tells you that like what is your mesh skewness, how much patches it has, moving walls, fixed wall, boundary condition. Sorry. First it will tell you see here points, how many points you have, how many faces, how many internal faces, how many cells, and how many faces per cells. It gives you every information, and at the end it will tell you about the your mesh quality. Checking geometry, it tells you about the mesh quality. We will not go deep into that. Now we have built our mesh. Now go to the paraform. We'll open it in paraview. And we do apply. So we in paraview you can also do this, like show patches names. It will also show the patches name. All right. So when we look at the mesh, this is how our mesh looks like. So you see, this is our block. So I have given only 0.1 in z direction. That is okay. So this is how our mesh looks like. So do you see? It has 10 number of cells in x, y, z, and x, y, and z direction. This is how our blocks look like. Now, so you are following up till this part. Now what we will do is we will look into every aspect like cell faces, cell faces, neighboring cell, patches and everything in one by one. So what for that, what we do is first we change the number of cells to one, right? Number of cells in X, Y, Z direction, we are keeping one just for the simplicity, just to understand something. Because when we try to understand from depth, we have to start from the very basic. So now we'll run block mesh again. So now we have run the block mesh. Now we'll go to the polymesh folder, all right? And now we'll open all these. So we'll look at the boundary at the last. First, we want to see the points. So you can see we have 8 points. And let's also open this in parallel. Let's not open it parallel. We will simply see by this. Now we have 8 points. And these 8 points are the same as these blocks. 0, 1, 2, 3, 4, 5, 6. These are also arranged in the same manner. So in points, it gives the point that we have defined. So because we have only one block here, so it is showing us the 8. All right. In the honors, there is only one cell center. So there is only one owner. And there is no neighbor, because there is only one cell. There is no interface cell here. The interface face here. All faces are boundary faces because we have only one cube. All right. So we are getting no neighboring cell. Here we have one owner cell. All right. And we don't have any neighboring cell. And faces we have, you see 6 faces we have. And these are the boundary, like the cavity test. We have moving wall, fixed wall, and front wall. So this n faces is number of faces it has. You see the moving wall is top one and it is only has one face, and front and back has two faces, and the fixed wall, that is the side and the bottom, has three faces. So this by this you can simply understand how the faces, neighboring cell, owner cell, and the points are defined. Now what we will do is we'll change. Now we'll go to the block mesh again, and we will change this to 5. Let's say 10. Let's change it to 2. Keep this. Let's change the number of division in x and y direction as 2, 2. And in z direction, we are keeping it 1. Okay. Now we'll again run block mesh. Now we'll open it in ParaView. Now we'll apply, and now if you look at the mesh here, you can see it is divided into 4 cubes. All right. So it is divided because we have only one grid in z direction. It is showing us the plane, and two grids in x and y direction. It is showing us 4 cubes, like 4 blocks. So 4 blocks, for 4 blocks, we have how many? We have 18 faces. For 4 blocks, we have 18 faces. All right. So now what we will do, we look at the points. We do reload. How many points we have? 18 points. Okay. And then how many faces do we have? You can, in this case, you can literally count your faces and points by hand. You can literally look into it. That's why I'm going with the very basic, very small grid size. So you can see 20 faces. You can even count 20 faces here by looking at this. And we have 18 points for honor. For honor cell, we have 20 honor cell. All right. For example, for each interfacial, so for each interfacial cell, we have 20 honor cell. So, so this is so this 0 is the cell for phase 1. So this is for phase 0. This is the cell for phase 1, like this. So for every phase we have is honor cell. All right. And in the neighbor we'll have we only have 4 faces. That is, you'll better understand if I put it like this. That is, for for a interface, for we have 4 interface, like we have 4 internal faces. You can see in the node part, we have an internal face as 4. So this is cell for the first internal cell, all right, internal face. This is the neighboring. One is the neighboring cell center or neighboring cell for the first internal phase. I hope you are getting me through till now and you are understanding it. All right. So similarly, this two is the neighboring cell for second internal phase. So we have so neighboring cells are always equal to the number of internal phases we have. And for every phase we have a owner cell. All right. So these are the simple things that you need to keep in mind. All right. I hope everyone is getting up till this. Now you can see that as we have updated the mesh, the the boundary patches are also updated. Now we have number of faces as 2, number of faces as 6 in the fixed walls, and so number of faces in the every boundary has increased. Now what we will do is we'll increase it just to show you. So now what we will do, we'll make number of bits in x and y direction as 2020, and we'll again run the block mesh. Now block mesh is run. Now if you look at the updated points, you see how we have 882 points. We have 1640 owner cells, and we have same number of faces. You see, the number of faces and owner cell are always equal because for every face we have to define an owner cell. For neighbor cell, we have 760. So for every internal face, that is an internal faces, we have for every internal face we have a neighboring cell, and you see number of faces. So by this you can always have a look and you can understand. So this is the beauty of OpenFOAM, that it lets you assess each and everything from coding level to, like, you can't see these things in other software like ANSYS or any commercial software, ANSYS, Converse, CFD console. You don't get to see like every information of the mesh. It will just tell you this is your quality of your mesh, orthogonal quality, skewness, and you just keep on changing it every time till you get a good mesh. But in this, you can literally go through everything, and you can also see that in the boundary patches, everything has changed. Now I want to show you. Now the next thing we'll see is that how the mesh is called in the like when we run a solver. So this is how the mesh work. You have created a block mesh. Now how it is called in the solver, how we can see it in the when we run like the solver command like icofoam. So I have downloaded this folder, that is understanding mesh, from Pratyush GitHub, and he already explained this in his YouTube channel. So you can also go through that. So you have already seen uh, that how we run a solver, how a simulation is run in blockMesh. So because this is C++ based, we always run in a main folder. So main function. So in this also, in similar way, you can see that we have a main function in which we are first doing this hash include set root case. So this will do is this will create an object which will look for an that is there is the structure of the folder, that is zero system and constant folder are well defined or not. So if there is the structure is not well defined, that like there is any of three folder absent, it will just throw you an error, that is fatal error exit. So this is to define to check the structure of the your test case. And then this is hash create time dot hash. This is to object to create a time object, that is it will create an object which will run the simulation iteratively or with time. Now we have, you can see, now this is where the finite volume mesh is called. So foam is a namespace. So foam FV mesh is where the there where the mesh is called. All right. So if you look at this, so this is like the solver to understand how the mesh is being called in the main function when we run the simulation. So here we have these files. So as you have studied in the previous class that this is how we define a new application. So this is a new application, or you can say a new solver. So we are naming it that form user AppWin. We are naming it understanding mesh. All right. And these are the libraries and include files we need to run this. All right. So what we will do is we'll go here. So we'll wmake wp. So we'll compile this solver because it is already compiled. So it is not doing nothing. We can clean it. Wclean.all cleans everything. And then we'll do wmake again. All right, you can see our solver or solver to understand the mesh is already is compiled here successfully. Now we go to the, let's say, now we go to the same cavity case. We go to the same cavity case. Now here we open the control dict file. The control dict file is where we define the timestamp, how we want to write our output file, and all these things we write it, and we write what application we want to run, what kind of solver we want to run, or what application we want to run. So you want to run the application that we have just made, whose name is, what is its name? Its name is this understanding mesh. So we copy this and we, in terms of icoform in application, we write this understanding mesh. Okay. Now we go to this cavity test case. We open it, and what we do, we have already run the block mesh. All right. Now what we do is we run the understanding mesh application. So this is application we are running, or solver we are running. So you can see it is showing us nothing. Now we want to see, although it has called, you can see here, although it has called the mesh, it has checked the test case, it has made the time object, and it has called the mesh. All right. Now we want to output. So how we access the cell center, the space, the faces, the neighboring cell, the neighboring cell and the owner cell here, how we access it. So we have, for cell size, we have mesh.c bracket. This function is for mesh cell size. This function is for face size. So you can look into here, it will be available to you guys, and you can see the function that are used to call the cell center, the face center, cell size, face size, and all these things related to mesh. Now we want to see, now we want to see, now we want to see how the mesh, what are the mesh point that we have, how many cells we have when we run the application. We want to output it. So we uncomment this part, and here you can see that uh, for every, we want to output the x, y, z coordinates. So for every cell. So what we do is here we run a loop and we output mesh.c, that is cell of the mesh I dot x at ith part, and that is the x dot x means we want to call the x dimension of that. All right. So what we do is first we have to recompile it because we have uncommented the mesh part to see the x, y, z coordinates of each and every cell. So we again do wmake. So you can see the wmake is successfully done, and then we again run the understanding mesh. So you can see that here we are getting x, y, z coordinate of each and every cell that we have. All right. In similar way, so you can always print things. You can always go to the dict file, polymesh file, see your faces, edges, faces, cells, and the internal faces and everything. Now we want to see the XYZ coordinate of our faces. All right. So this is for faces. So mesh.c is for cell center or cells, and mesh.c CF is for CF is for faces. All right. This again. So this will print us the coordinates of faces, I think. Yeah. So here it is printing only the x coordinate of, so you can print it just. So you do, so this, C file that Pratyush had made you can like keep commenting and look for any information that you want. So for example, in this part, you can see that he has, you can see the information about mesh neighbor size. So neighboring cell size, you can see in this part, you can see the patch, boundary patch. So So you can keep on going and exploring that we have explored through these things. So we have already explored everything through these things. Like we have seen faces here, neighbor, owner, endpoints, everything. You can always go and print this to a application, or if so in like you can change your change you do changes in application to see the mesh printed on your screen when it is running. Okay. So there are a lot of things that you can see. You can loop over boundary patches and you can try it yourself. For example, let's do one thing. So you can also see the size of the mesh, okay? Size of each and every cell, and you can also look at the information of the boundary patch. So again, because we have done some changes, we'll compile it. Let's clear it for now, and we'll do understanding mesh. So you can see that patch 0 moving wall. So this is the information about uh so this have information about cells. At the topmost position, you'll have information about the size. You can see the size. Mhm. 1 second. Info. So the first one is only printing the mesh has these many cells and mesh has these many internal faces. So first command thing is telling us how many cells and internal faces we have. Then we have XYZ coordinates of each and every cell in the domain. And at last we can see patch 0, 1, and 2. That is, we have three patches. First is moving wall, which has 20 faces, and the start face is 760. Same information we are seeing through this. Right. So boundary patch, when we go through it, we have moving wall, number of faces is 20 and start face is 760. The same thing we can print through the application. Then we have fixed wall, then we have front end block with 0 faces. All right. 1 second. Why it is showing 0? So there is, yeah, so this is it. So you can either go through these to see the information, or you can also print it. So there may be cases when you are running a solver and you are getting divergence at some point. So you would want to see at which mesh size, at which mesh point it is giving us the error. So you can always print the coordinate of a mesh point, which is like the starting of your divergence issue in your simulation. So these kind of things help you in debugging your simulation when you like whenever you want. All right. So this is how I have shown you how to navigate through boundary patches, faces, neighbors, owners in the polymesh file, as well as through printing through an application. All right. So now we'll move ahead to the other part of the block mesh. Okay. I hope everyone is understanding this and getting through everything that I'm telling you. So now what we will do is we'll go to the same folder, cavity, and we'll open the blockMeshDict file again. So we have defined 20 in x direction, 20 in y direction. Now we want to see is in a few cases, what you would want is in many cases, what you want is you want fine mesh near the wall and coarser mesh at near the, let's say, the in where the bulk flow is. So near wall you always want a fine mesh. So this is simple grading. All right. So how it is used is, so when we have one, it is uniform mesh. When we change it to 0.1, so 0.1 tells us the ratio between the first cell and the last cell in the x direction, first one, and in y direction is the second one, and in third direction is similarly. So now we have changed this to the 0.1, 0.1 and 0.1. That is, the first cell will be very smaller as compared to the 10 times smaller as compared to the last cell. And now we'll run the block mesh again. And we'll see the mesh in the para view. So you can see that. So 0.1 is actually opposite of this. That that is the last cell in x direction is 10 times smaller than the first cell. And in y direction, you can also see that the last cell in y direction is 10 times smaller than the first cell. Now we can do this opposite of this. This is basically used very much in when we have flow through a channel, flow through a pipe, where you want smaller mesh, smaller mesh size near the boundary layer to resolve the boundary layer. And this is very much important in this turbulent flow, where we want to resolve the every eddy that you have near the wall. Now we'll again run the block mesh. Now what we have done just the reverse of that, right? So you see the things have changed. Now uh, the first shell is 10 times smaller than the last shell. All right. So this is just the opposite of that thing. Now the next thing is when we have multiple blocks. So here you have understood how we define vertices. In blocks, you have understood how we define the block using the hex command, and we have how we do distribution in x and y direction, like number of grid size in x and y direction. And you also understood the simple grading. Okay, so now we'll move to the now faces and patches. How to define faces and patches. Not now what we will do is go to the same block mesh. So here we have defined the boundary, that is patches that we have to define. Now till now it was giving us no error. All right. So we were just typing block mesh and giving everything better. You see here it is saying us the patch 0, patch 1, patch 2. All right. So now what we will do is we'll switch this 4 to 0. So now we have the so in this not here, let's do this here. So now we have switched the points 7 with 3. That is, the points are same. The points have not changed, but we have changed the orientation of the point. So there is a typical rule to how to define a face. So we have like now changed this. So this is not as per the rule. So let's see what error we get. All right, it is still not giving this. All right, let's clean our mesh. Mm-hmm. Mm, 1 second. So now, okay, now I'll teach you that how to define the faces. So for to define the faces, so for example, you have this top and bottom face. All right. So the bottom face is how we have defined the bottom face here is uh, 0. All right. So how we have defined the bottom face is this. That is type wall. That is 1, 5, 4, and 0. All right. So we have defined our bottom face as 1, 5, 4, and 0. So if you curl your hands in the orientation, you'll see your thumb will go to the toward the center of the block. And similarly, when we define this top face, that is 3, 7, 3, 7, 6, 2. So you see orientation of the bottom and top faces are opposite, such that when you curl your hand in the direction of orientation of the face, it is always go in the same direction. Either it goes outward or inward. So for example, at the bottom, when you curl your hands, it is going to the center of the block. And the top, when you curl your hand, that is 3, 7, 6, 2, it is going toward the center of the block. So whenever you define faces, you keep these things in mind. So in this, all right, so we'll just see that. So what error we are getting here is, so what I have done is I have defined a wrong face. So 7023 is not a face at all. All right. 7023 is not a face. So what it gives us the error is deleting polymesh. Okay, creating block mesh from this. So it is saying face 0 in pair 0 does not have a neighboring cell. So when you uh, define a face that is not there, or we define not properly define a face, or define a face which is not there, basically you will get this error that there is, for that internal face there is no neighboring cell, or there is no honoring cell for some face. So so you have to, so here I by like I have changed this, so I'll change this to the correct face, that is 3672. So this is the exact face, that is the top face, that is this top 3672, 3672. No, no, no. It's 3267. 3762 basically. Yeah. 3762. Now we know that everything is correct. Now we'll try to change the orientation of top and bottom block. So 3762 is the into the orientation into the block. And for this 0154, we'll do for the bottom face, we have 0. Sorry, what if we have 1540, that is anti-clockwise, we'll do it clockwise, that is 1045. Let's see what happens. 1054. Is it correct? Sorry. 1045. I'm sorry. 1045. Block mesh. Okay, so block mesh is not giving us any error, but I think when we run it, it will give us some error, I think. When we run the application, it should give us some error. It is not. So 1 second. They're still not giving us error, but I have seen some cases in form extend in which it might give an error, but so I look into the if this so if it is not giving an error even in the block mesh part, in not in the block mesh, and so you can see typically see here that the orientation of 3762 is 3762 and 1045 are both the same. So it means orientation does not matter. So we'll confirm about this rule, but this rule in the later session. But just keep in mind that you have to have some orientation of the faces, otherwise it will throw you some error. I don't know why it is not giving an error. I'll just uh, hello Pratyush, are you there? Okay, well in the next session uh, we'll again go through the rules for defining a face. I think both are working in case, but in some cases I have seen it like in form extend version, these gives problem. So, but more or less you can see that you have to have some orientation of the face. You can't just randomly put it. Okay. So next we'll go to the next thing is in block mesh is what? So you can also see the flow. Let me show you the flow. I have run this. So you can see this is not the good like right result, but you can see the solver running here on this mesh. All right. The next what is the next thing is the next thing is how we define the faces. Next is the next thing is how we define the edges. Okay, so this is typically how we define the edges in block mesh. So first thing is straight line, that is simple. Like you have a straight line. The second is arc, circular arc that needs a single interpolation point. Then we have simple spline, that is spline curve that have list of interpolation point we have to define. And we can also define a polyline. So between the two points, you can always go keep on, you can always obtain any complex surface that you want through these simple splines and polylines. All right. So for now in this lecture, we'll only go to the edges. We'll only see about how we define an arc, how can we make an edge go circular. Okay, you can always look into the more complex cases if you want to. You can look into simple splines and polylines also. For these cases, you need multiple interpolation points. So now, so now here we have a block. So this is the case basically. So this is the block. Okay. So now if you want a cylinder, now if you want a cylinder, then we have to define the edges, curved edges for 1, 2, 2, 3, 3, 0. We have to define a curved interpolation point and edge for these four edges. And similar for the back edges, that is 5, 6, 7, 4. All right. So here I'm just showing you that is we have a edge, we have points like 0, 1, 2, 3. And for face, for edge 0, 1, we have this arc 0, 1. And these are the interpolation points. This is the interpolation point basically. That is in x direction we are at 0.5 and y direction we are at minus, this is below this. So we have minus 0.2071. All right. So similarly in the right hand side we have this edge 1, 2 and we have this arc 0, this should be arc 1, 2 and the corresponding interpolation edge. So when we make a curved edge for 0, 1, 2, 3 and 4, 5, 6, 7 edges, we get a cylinder. Okay.
Abhishek, there is a comment in the chat box.
Okay. Okay, your faces.
So basically, the
No, no, no.
orientation should be outside, but it is inconsistent with the. We have shown the examples. That is what someone is
Of
saying.
the face, right? Of the face. Orientation of the face you're talking about, Pratyush.
He is saying that the orientation should be outside,
Of the
but
face, right?
of the face, yes.
Mm.
But maybe you have shown
No,
some
no,
example.
actually, the thing is, this is very complex. I have seen in some form extent cases, in open form, you see, this is not giving us any error in these version of open
See,
form.
as soon as I know, as long as you are not running the SRF or this rotating frame kind of examples, then there will be
Hmm.
no any issue. But
So,
when you are going to use the cyclic or rotating frame kind of examples, then it is going to show you error.
yeah, so block mesh in simple cases, it does not, is not throwing an error. But if you go to the complex cases, it might throw you an error. So you have to make sure your orientation of faces is correct. And about this, uh, the numbering of vertices, number of vertices is correct. Number is of, Pratyush, am I right?
Yes, Abhishek.
A number of vertices is not wrong. Number of vertices is correct. The example that I have shown you.
So yeah, please show the dict file.
Yeah, so the number of vertices and this, like, hold on. This first we move in X direction, then we move in Y direction, then we complete the plane, and in the same starting from the same starting point, move in third direction. So this is the typical how you define a block, and this is not wrong. This is correct. Even this that part that face orientation is also correct, but in some cases, there are like it does not throw in error in simple case. That's it. Yeah. So the moving wall, that's what I'm telling you. In this case, like I have seen cases where pointing outward and pointing inward both are not giving us the bad result. So I've seen just shown you that either it is pointing outward or pointing inward, it is not giving us an error. But as Pratyush said, in some cases, it may give
So
when it is
in the
pointing
case of the
inward.
rotating frame, you have to point out the direction.
Hmm.
So in that scenario, while you are going to point out the direction, so it assumes that the face is already pointed out the outward direction. So that is why in the case of the rotating frame, this is very important factor that you should take this rule that the face orientation should be outside.
I have also got.
We will cover this while we will move to the mesh movement kind of example. So
So make
this
sure that. Yeah, Pratyush, go.
this is just a basic static examples. So don't
Yeah.
worry
So.
about.
Hmm.
Yes,
See,
yes.
you should have in mind that there is an orientation, and in complex cases of dynamic meshes. So I got this error in inverse boundary methods. So I spent a whole lot of time figuring it out because in some cases it was working in both sides, but now it is like in some cases it does not. So I hope the confusion is clear. Let's move ahead. Yeah, the rules is simple. Yeah, we'll clear it out next, but you simply have to point outward the face. Rupak, we have to point outward, but yes, in this case, it is not throwing an error. Now we'll move to the edges part. So how we define the edges as we were discussing. So this is how we define the edges. We have to define an interpolation point. So for that, I have made it test. So you can do is you can open that block mesh only, this block mesh. You can go and defining your edges. So first you have arc. So you have arc 0, 1, arc 0, 1, 1, 2, 2, 3, and arc 0, 3. Arc 0, 1 and the interpolation point. You can keep on just copy paste. So we have arc 0, 1, 1, 2, 2, 3, and 3, 0. And we have interpolation point at 0, and then 0.2057 and 0. Next interpolation point is 1.2057. Next direction, why we have. Let me just copy it paste from the other case that I have already done. All right. So, so here I have defined a circular arc for these front faces 0, 1, 2, 3. Now I'll do the same for the rear face. All right. So what we will do is copy this and paste it. And we have, all right, now we have this. What we usually do is the back face is always same as the front face. You just have to define this point 1. And this will be, from here you can see 4, 5, 5, 6, 6, 7, 7, 0. It's better doing this way. 4, 5, 5, 6, 6, 7, and 7, 0. So now we have defined the arc, and now we'll run the block mesh. From this, for the same folder, for the share cavity test, we are running block mesh again. Okay, to give me the bug topology. There is patch inconsistencies that I have done some mistake in there. Hold on. Okay, so this is should be 7. Let's see, okay. There is some mistake in this that I have done. Let me see one. Oh, so I was looking at this different. So this is 7, 4. So this is basically 5, 4. The back face is 4, 5, 5, 6, 6, 7, and 7, 4. Now run it. Okay, so you can see that we have successfully like given curved edges to our cavity mesh. Okay, so now we look how it looks in. So this is your block is formed. You can see what one thing is there. So uh, let's keep simple grading as 1 for this case and increase the We'll again run the block mesh and so you can see you get this cylinder, okay? And we look at the mesh of this. You can see we have made a cylinder which have only one grid. We can give multiple grid in Z direction also. So you can always do that by changing this, All right. All right. So basically this is simple geometry. You can always give multiple multiple number of grids in Z direction. Okay, so you can just do this by, let's say 100. You give it 100 and run block mesh. Now let's see it. बढ़ा दे. So this is how it looks. Let's see how the mesh looks. So you can see that we have made a cylinder with 100 number of grids in X direction and 20 grids in X and Y direction. The problem with this is you can see that here. So mesh is kind of distorted. Near the wall, the mesh is kind of distorted. You can see that. So this is not the desired mesh that we want. Like, okay, so the near the wall, the mesh is distorted and the mesh will have a lot of skewness. So if you check it, so we do this check mesh. So if you look here, mesh skewness is 0.9944. That is not good. So what we want is the skewness should be as close as 0 and mesh orthogonality, that is, it should be defined somewhere here, is not. So mesh non-orthogonality maximum is 75. So mesh orthogonality should be larger, but the mesh skewness that we have should be close to 0. It should be as less as possible. So when we are defining a cylinder, the point is the way the X and Y and Z grids are defined, it is not like simple to make it. So this cylinder is not, so this is not a desired mesh for flow in a channel using a cylinder. Now if we try to like give simple grading, let's try giving this. Try simple grading. Like that is we want in X direction, we are uh, refining the grids in X and Y direction, and we are keeping it constant in Z direction. And we run block mesh. Now we want to look at. Now if you look at the mesh, so you see Z direction is okay. There is no problem with Z direction. But then the direction that we have give curved is, see, you see we are getting this more skewness. The mesh is getting, like mesh is not good. You see, so when we define the edges, we have to make sure that in X and Y direction, when we give simple grading, how things are turning out. So X grading is only in X direction and it is in Y direction. But here you can see it is not turning out good. So how to make a cylinder which have such that we can, so there is a method to make a cylinder in which we can define, in which we can get like finer grid near the boundary and coarser grid in the bulk flow region. So if we do like check mesh, you can again see that check mesh, you can see the skewness is not good. max skewness, it is very large. Skewness is very large. Mesh 1 mesh check failed. Failed 1 mesh check. So mesh check is failed that skewness is very large. 40 highly skew faces detected which may impair the quality of the results. So you can see that the mesh quality is not better. So this is not the right method to make a cylinder from the block mesh. So this is where the multiple this is so now if you want to define a to make a cylinder using the block mesh, what you have to do is you have to go through a multi-block system. What we do in multiple block is we have to have multiple blocks. Okay. So here, so this is the case. This is how we make a axisymmetric mesh for the cylinder. So we have here we have 5 blocks. The central block is 1. The right side this block is 2. Top is 3, 4, and 5. So central block is kept as a simple cubic block, and the right side we have these blocks, and on the right edges we define the on the right like on the extreme edge we define the a curve through which we can make a cylinder. So in this case uh, in this case when we give simple grading in x direction, it will refine this. Okay. So I have already made a one case. I'll just show you, and then I'll show you test case with I will make a test case with 2 blocks. Okay. So now we'll go. I'll just show you the mesh blockMeshDict file and show the mesh using this multi-block system. That is, we have 5 blocks. Center is 1, 0, 1, 2, 3, 4. I have already made it. So I'll just take you through that. So we have a mesh. So we have a mesh which I have. This is not the.
Sheikh, there is
This.
noise.
So we have a mesh which have, you see, 5 blocks. All right. So we have, if you look at this here, we have like how many? 1, 2, 3, 4, 5, 6, 7, 8. 8 front, 8 behind. We have 16 vertices. So let's see. So we have 16 vertices, right? So okay, we have here like 18 vertices. Okay. So we have 80 vertices and we have what? 5 blocks. Yeah, we have 5 blocks, that is 0, 1, 2, 3, 4. So we have 5 blocks. The first one is internal and other 4 are the outside blocks. And we have defined these arcs. So these are 4 arcs, simple to the previous case. So we have defined how many? 1, 2, 3, 4 arcs from the front and 4 arcs from the back. And these are the basic definition of the patches. This is the same case. So this is basically flow through a channel, circular pipe. This is the flow through circular pipe mesh. And we have here inlet patch on the left, outlet patch on the right, and then wall, the side walls. Okay. So we have here, you can see 5 blocks. And when we run it, we'll see it along with the patches and we'll apply. show patches names and apply. So you can see we have an inlet and outlet and a wall. If we zoom in into this, you can see a mesh, and when we you can see a pipe flow, inlet, outlet, and wall, and we look at the Z direction. What I want to show you is this. Now you can see, now you can see here we have uniform. In the we don't have that skewness that was coming in the previous case. So now we have uniform grid near the wall. So we can also get simple grading, and this will give us fine grid near the wall and normal grid in the outer blocks. You can normally see that 5 block, the center block, the top, left, right, and bottom. So in there are various cases in which we have to like define multi-block system, maybe 8 blocks. So for if you can also simulate flow over a cylinder, circular cylinder, in which you have to make maybe 16 to 20 blocks. So we have always have to define multiple block system. All right. So if we try doing this, try doing what? If we try to do, I don't know how it turns. I am not tested. I'm just trying it. I'll try this. So this is it. We have multiple blocks. Now we'll solve a system with 2 blocks. Okay. So there are cases where single blocks is we need to have a multiple block system. So what happens in multiple blocks is either you have to by default like make sure that the two faces are matching, or you have to merge the two faces. Okay. So there is also a concept of face merging. For now, we'll look into the face matching part only. We have block one, we have block two. So now we'll name this block one, block two. These make sure these faces are connected. Okay. So now how will go this one, two, this is 0, 1, 2, 3. Now this will become, now this will become 1. So what we do in face matching, what we do is the right hand side face of the first block should match the mesh and the size of the left hand side of the block 2. Now we have 0, 1. This will be 2. So 0, 1, 2, 3, 4, 5, 6, 7. Here we have 1, 2, 3. So this will be 2, this will be 5, and this is 6. All right. Now in these cases, let's define the length as 20. 7, let's name this 8, 9, 10, 11. So Nothing will change. This will becomes 0, 0. So now what we have is, what we have two block system in which we have on the left one block, two on the right second block, and the interface that is in the internal 1562 has to be matched. Okay. So first we'll see how to define two blocks and how to make sure that edges for the both are the same, both are equal. So not wow, what we have defined to define is 8, 8, 9, and 10, 11. Okay. So now we go to the same cavity folder. Now we go to the same cavity folder. We comment out this R because we don't need this for now. Now we have to define the vertices. Now we are adding 4 extra vertices. Now 8th point has, it is 2, 0, 0. 9th is x2, y1, that is 10. Next we have 2, 1. And lastly we have this 11, that is x2, y1, and this is 0. So now we have defined these are vertices. 8, 9, 10, 11. Now in similar way we'll define block. This is left block, this is right block. Now we'll have to define the left block, that is how we go 1, 8, 11, 2. Okay. So now we move in X, we move in Y, and we complete that train. 1, 8, 11, 2. And there is a possibility we'll get a lot of errors in this, but figure this out. 1, 8, 11, 2. 1, 8, 11, 2. 1, 8, 11, 2. And then we go from 1, we go in Z direction, that is 5, 5, 9, 10, 6. 5, 9, 10, 6. This is how we define a block. So let's cross check each and everything that nothing is wrong. So we have these simple vertices that we have already. Now we are adding blocks, so we have to add 4 vertices on right. Okay. So in next direction we have 2 for everyone. In Y we have first is 0, 0, 0.1, 0.1, and 0. So it means in Y we have 0, 1, 1, and this will be a 0. In Z we'll have 0. Zero, zero. Okay, so we are just cross-checking it. In Z direction, we have a 0, 0.1, 0.1, and 0. So middle ones are the width. I think it is okay. So let's run it now. Same case, block mesh cavity. Okay, so there is some error now. Hold on. Okay, so it is giving us some error. Give me 2 minutes, I'll be back. Just one. Sorry, everyone, that was emergency call. Now we are getting some error, I think. So you have to cross-check everything, okay, one by one. I don't see any error by the way in the vertices part. Vertices seems good. Now let's look at the hex part, the block part. Block is 1 8 1 8 11 2 1 8 11 2 5 9 10 6. Is also good. Good. Let's remove the simple grading for now. Okay, so what it is saying is, if you read that error carefully, it is saying trying to specify a boundary face 2561 on the face to cell to on face on cell 0, which is either an internal face or already belongs to some other patch. So what we have done is we have 1562 is and now have become internal patch because we are defining it two blocks and this is a common between the two. So this are no, but we are here. You see this patch 2651. 2651 we are defining as a boundary patch. This is not it can't be a boundary patch because it has now become an internal phase. So the point that we are trying to tell here is when we are doing multiple block meshing, so we have to have and by default matching of the mesh between the two faces. So these connecting faces of the two blocks should be same. So if we comment out this, okay, so our block definition I think is correct. If we comment out this, we should get this. You see now meshes. So what the problem was is we were trying to define an internal face as a boundary patch, which is this is the definition of the boundaries. We can't define a internal patch as a boundary. So if you look at paraform, this will be a simple mesh. Will look simple as that. So this is simple uniform mesh. You see there is not much change. The point is here we have two blocks. All right. So in cases when we don't have by default face matching, we can also always go for face merging. So this is what face merging looks like. So in this, you can see in one block the mesh is very coarse, and in the adjacent block we have very what do you say fine mesh. So face merging is used when the default matching between the two edges is not met. All right. So let's try this face merging merge patch pairs. Hmm. Let's define this here. So I was not prepared to do this. It's okay. So merge patch pairs will do the next class because it will take quite a while time. And so the point is, if for example, so we have x 20 grids in x and y direction, and z direction we also have 100 grids. So let's say I change this to 50. So in z direction I have 50 grids in block 1, but in the block 2 I have 100 grids. Now if I do block mesh, it will throw me an error. Okay, so inconsistent number of faces between block pair 0 and 1. So to solve this, we use face merging. Okay, so this merge patch pairs can be used to solve this. So in that case, we have to, in that case, what we do is, in that case, we don't define these 1, 2, 6, 5 faces are the same. We have to define it differently. So these faces 1, 5, 6, 2 will be defined differently. For example, we'll name this 8, 9, 10, 11. All right. Sorry, 8, 9, 10, 11, and 13, 14, 15, 12, 13, 14, 15. So we have to define each and uh, every face of both these blocks differently. And then we have to define the pairs of the faces that we want to merge. Okay, so in that case, in those cases, we can do that. So so now there is one more thing that we can dynamically define. So for example, uh, there is one thing. So for example, if I want to change this, I want to change this 10 to 100, then I have to go and manually change this to 100. And so here I have only like how many? 12 vertices. What if I have a very large mesh? For example, in this case. So in this case, you see, I have a lot of vertices. Even in this case, I have only 18 vertices. In some cases, which I have made mesh, is you go up to like 30 vertices or 40 vertices. In those cases, if you want to change the mesh size from 10 to 20, you can't like keep on going and changing it. So in the such cases, there is uh so if you want to dynamically so change the mesh, then you can do it. Like there is something dollar x equal to, let's say, 10. I think the syntax I'm not getting it. Let me Google it. Yeah, so this is it. So you can see here, we can always define things like this. That is x min equal to 0. You can like write it. So if you go here, we write z max, z max equal to 0. And in place of 10, we can write dollar z max. Okay. I think it is the right syntax. Let me just confirm it. Yeah, it is right. Dollar z max, and yeah, it is right. Okay. So z max we have defined it. So we have defined z max equal to 10. Let's say z max is 1. Now we run block mesh. I think there is some error with the block syntax of this. There is no equal to sign, yeah. So there is no equal to sign. We just have to write it like this. Yeah, x z max equal to 0, and then we do block mesh. Illegal dictionary entry. Hmm. Should be out.
The Z should be outside the vertices
Okay,
box.
okay, okay. Yeah, yeah, yeah. Sorry for this. Yeah, now it is running. So you can dynamically change. So if you look at the paraform, you will see that the direct length of the, you can see that in Z direction, the length has reduced. It is only one. Okay. So in this way, you can, so when we have like too many number of vertices like this, so it is best to dynamically define like this. Okay, so Z should be outside the vertex. Yeah. So you can simply also do that for Z min, and you can define it like 0.1 or whatever you want, and you can dynamically change this. So I think this is all from the block mesh side. This face merging thing, this face merging, if I want to teach you this face merging, it will take, we have to define two blocks separately. That will again take a lot of time. So I think this is enough for today. If you have any question, then you can ask right now regarding this, whatever we have learned today. So this face merging part and some of the rules of that, how we define a face, that is finalized, that it is always should point outwards. The thumb should always point outwards. But in some case, I think that is clear. The the rule for the face pointing outward is clear. Can you open that understanding mesh and tell about the mesh object creation? Yeah, so we have defined only simple grading here, so we don't have time. Multiple grading will take time, so I think we don't have enough time to discuss multiple grading. We'll cover that multiple grading in the next session. Yes, yes. The merge patches and actually multiple grading people have not, people do not use that much. So this is because introduction of the block mesh, so will not go too much of the complications of the block mesh right now. So merge patches pair will be covered in the next class. Yes. So who is this Akshay Pool? Can you open that understanding mesh file and tell us about object creation? So mesh, wait. So the for the object creation of the mesh part. So this is where form FB mesh. This is the where object. So when we do this hash include create mesh.h, it creates the object of the object of the mesh, and this is where the finite volume mesh is called. That is where the object of the mesh is created. And so in most cases, we only have this command, that is hash include create mesh.h, and it is mostly written outside. We have a create fields. So in create fields, the object of the mesh is created, but here for the understanding, we are creating it only in the this file. And you have to, if in order to access this cell center, face center, and information about the mesh, you have to create this object. So this is where the object of the mesh is created. Here, the test case or your set root case is tested or checked. Here the object for the runtime iterating solve is object is created, and here the mesh. I think it is clear. Yeah, I will share the PPT presented. Yeah. So the thing is, if we start covering the merge patch pair set, I'll have to make. I have not made already the block. I have not made the test case already. So I have to make it right now. So it will take time. Yeah, I have to define two different. Then so have this week. I hope this week is clear. You can this. I will like up give this test case, that test case of the mesh of the cylinder, and you can try running flow through that. Flow through a cylinder or flow through a pipe using that mesh. Any other doubt you want to ask, you can ask me or Pratyush or Nikhil. So the you will get better in block mesh if you keep using it. Otherwise, you'll forget it in the for the. It is important for the when you'll start doing your own project. So keep keep testing or keep practicing the block mesh part. So that's it, guys. If you don't have any questions, so we'll finish it off and cover the rest block mesh part. If you want some extra assistance on the block mesh or want to learn extra, then you can ask us anytime. We'll cover it in the later sessions. Yeah, so actually you can import the mesh using design modelers geometry mesh. You can also make geometry in Gmesh, Gambit, and lot of software are there. You can always import, and it is very simple. Basically, it's not that much. So actually, today is the basics of block mesh. So when you have to import mesh, then you'll have to first understand how we define the patches in the NC design modeler or Gmesh. Then to convert it to the open form part is very simple. You have to just run one command. The hard part is to successfully define the block mesh in NC design modeler or the Gmesh. Wherever you're making the mesh, you have to make their mesh like you have to define everything properly. Otherwise, it will not convert successfully in open form. So converting in open form is simple, but making that mesh in other software carefully is important. So Akshay, yeah, we'll do that, no problem. So we can like give a simple tutorial if you want, basic from ANSYS or from Gmesh to OpenFOAM. I hope it is clear, Akshay. Today our basics of block mesh, so I think it is basics are clear.